Good, good morning, good afternoon, depending on where you're based, and welcome to this webinar about innovating thermal designs using TPMS structures. I hope you can all hear me well. If not, please let me know in the chat box. All right, let's jump into it. I'm Niels Verdijck. I will be your host today, and for today's webinar, I will be talking about the following points. Starting with, of course, what are TPMS structures? So what does it stand for, the acronym? How to efficiently use them in thermal design or in the thermal design process. I will talk a bit more about implicit modeling, and I promise that will be the end of the technical part of the. We will then apply it on a case study or two case studies, and if we still have time, we'll then do a Q&A session before closing off the webinar. Let's start at the beginning. What are TPMS structures? So TPMS is an acronym that stands for triply periodic minimal surfaces. Basically, it's a geometry where the surfaces repeat in 3 dimensions, x, y, and z. And they are defined by a single implicit function. The real benefit or the real applications of these TPMS structures are as follows. Firstly, they have a smooth transition between repeating elements. Basically, if you have a TPMS element and you place another one right next to it, independent of where it is, the connection between them will be smooth. And they're widely applicable, or they can be adapted, to stress, fluid flow, and heat transfer problems. They also have interesting mechanical properties, but this is still an active research field. And here are some of the common examples that you can find with TPMS structures. I'm sure if you look online on LinkedIn, for example, the top left one, the gyroids, you'll for sure have seen them before. Is the most common one, or the most marketing relatable shape. But you also have Schwarz elements, Neovius elements, diamonds, split B, and lindenoids. And these structures, or TPMS structures in general, find their use because they have a very low thermal resistance. It can be as low or even lower compared to pins. And they heavily promote mixing. As you can see, these shapes are not a continuous structure. They don't follow the fluid flow. They basically break up the boundary layer, which allows for mixing, which, as we all know, is very good for heat transfer. And they have a high volume. They have a high surface to volume area, meaning that you have a lot of contact area between the solid structure and the fluid. And as you know, contact area, that's where the heat transfer really happens. So that is, of course, also a plus. There is a bit of a price to pay. Firstly, as you can imagine, these structures are quite dense. They result in a lot of in a quite high pressure drop, and they have a very high design complexity. You won't sure be able to mill these structures. You will have to go with additive manufacturing to go. Let me quickly have a look in the chat if I'm all audible. Yes, you are. You can all hear me, so I will continue. Okay, that's everything I wanted to cover about TPMS structures. And now let's look at the way on efficiently applying them. Because TPMS structures have a pre-described shape or pre-described design pattern, the most intricate or the easiest way to tackle them or to optimize using them is a parametric study. Basically, a parametric study, you a priori define a given set of control variables, basically the variables that define the shape. And a parametric study is very easy to set up, but requires remeshing after every iteration. And it can become quite computationally demanding. But the benefit, of course, you can get a true CAD geometry, a true CAD part out of the parametric study. What are some of the computational challenges using parametric optimization? As I mentioned, if you adjust the dimensions of the shape or the geometry slightly changes, you have to do a remeshing process. And as a result, the adjoint methods cannot be used. So you can't use derivative calculation to find the best shape or the best possible solution. So you must use, in your optimization algorithm, you must use a derivative-free approach, a derivative-free algorithm. But let's put that now into practice. How do parametric optimization studies work? You basically start from an initial model, and then your optimizer should ask what-if questions. What if we change this, for example, the boundary conditions, or the heat transfer, or what if we change the manufacturing processes, or if you change the material usage. Based on this, your optimizer should build a wide base of all possible shapes, really explore all the bounds to see what works well, and to then use that information to find the best possible heatsink. As you can imagine, the amount of variables can quite easily build up or grow exponentially, and meaning that performing that study manually will become infeasible. In real-world applications, you easily have hundreds of design parameters. If you, for example, have 100 design parameters, that would require over 10,000 different designs to cover all combinations, and that's simply not possible in a manual fashion. That's why you will have to look for basically an automatic approach. How does a parametric optimization work? I'll first explain it with more conventional cooling shapes. It's a bit easier to do so, and then later on I will switch it back to TPMS structures. Let's consider three very common two-dimensional shapes: a simple circle, rectangle, and a diamond shape pattern. And for each of these shapes, you simply define the control variables. So for the circle, it's of course the radius or diameter, the height in the perpendicular to the plane, the spacing in x and y. So basically the repetition in x and y. Similar for the rectangular shape, you have the width and the height. The width and the length. Again, have the height and the density or the spacing in x and y. And for the diamond shape, you have exactly the same: the width, the length, the height, and the spacing. With these three simple shapes, you already have 14 variables, and that can easily increase to many more. So you basically have to find a more clever way of tackling this problem, and it's where a unit cell approach can be used. So this is a unique process developed by Diabatix, where you basically break the heatsink into a simple unit cell. So rather than having a circle or a rectangle or a diamond shape, simply have then a unit shape where the shape is a variable, and you're only left with the parameters that govern the unit shape, the unit cell, sorry, being the height, the width, and the spacing in x and y. So you simply reduce the complexity from 14 to 6 in this particular example, making it much more manageable for any manual or automatic process to test or to get a wide variety of or to test a wide variety of different shapes. The only thing that you have to do is repeat the unit cell within your design domain. So the houses look like from a quite abstract view. You have your optimizer, of course, your optimization algorithm that proposes some variables that, of course, needs to meet upper and lower bounds. Based on these variables and the bounds, a profile is proposed. Based on this profile, a geometry is created. This geometry is then transferred into a CAD file, be it a step, be it an STL, or any other CAD geometry. You prepare your overall geometry, so your heatsink, for a performance study. You actually perform the performance study using CFD or correlations. CFD, of course, if you want to have it more accurate, correlations if you want to have quick results. You evaluate the performance, temperature, pressure, etc. You feed it back to your optimizer, and you loop through this until you basically have found the best feasible design. And this allows you to quite easily and quickly generate a bunch of different data points and to test a wide variety of different heat sinks. Let's circle back then to our TPMS structures. As you can imagine, if you purely look at the TPMS structures, they're very complicated. So the amount of variables that you need to propose or need to generate to describe those shapes, they can easily increase to way too many structures. While using the unit cell approach, the amount of variables simply reduced to 3. Firstly, the size of the unit cell. Is a big unit cell with meaning that you only have a handful of structures, a handful of the design domain is filled with structures, or you have a very small unit cell, right? Meaning that you can repeat the structure quite often. That's the first variable. Second variable is the thickness. So for example, for a given unit cell shape, how thick are the structures within that unit cell? Is it small? Is it small thickness, like the one on the left? Or the structure is quite thick, like the one on the right? And lastly, of course, what shape do you want to consider? Do you want to consider gyroids, lineoids, split P, any others that you fancy? Those are basically your 3 variables that the optimizer can change. You of course define on the upper and lower bounds. All right, so that's everything that about TPMS structures and how to efficiently use them in the design cycle. Let's now talk a bit more about implicit modeling. As you see with our TPMS structures in general, again, have a very complicated shape. And by representing them using conventional tools like STL geometry or BREP representation, those techniques rely on basically stitching together different surfaces. With STLs is triangles. And if you want a very high resolution of your step file to easily capture all of those details, you need a very large mesh count and a very large number of facets. And the more facets or the more triangles you include, the easier it is that an error sneaks in. But this can be prevented by using implicit modeling, where basically your complex shape, your complex geometry is represented by a simple or relatively simple equation. For example, here, if you look on the top right, this rectangular beam is basically represented by this function. This sphere represented by this one, and this cube can be easily represented by this function. Implicit modeling also allows for easy Boolean operations. For example, if we take our rectangular beam again and our sphere, by using a min function, you basically perform the successful Boolean operation of those 2 structures. Another very interesting or very useful feature of implicit modeling is it becomes very easy to calculate the distance from the boundary, as well as to calculate if you're on the boundary or outside of it. If you're inside the geometry on the interface or on the boundary. For example, if your function value is negative, meaning that you're inside of the structure, you're in the solid part. If your function value is 0, you're on the interface, on the surface. And if you have a positive value, basically that means you're outside of the structure. You're in the fluid domain. So in short, the benefits of using implicit modeling are as follows. It's a very simple boundary detection, so you can easily determine whether you're inside on the surface or outside. It allows for efficient Boolean operations. You can easily, for example, perform a union of 2 shapes using a min function. It's also it's also very reliable. You can easily create fillets and blends, and it's highly scalable. Let's look, for example, to what an implicit modeling or what the function is to represent a gyroid. It's this relatively simple structure to represent quite a complicated geometry. And as a reminder, gyroids have a very high surface to volume ratio and are fully self-supporting, which is of course a nice positive. And as you can imagine, also fits quite nice in the unit cell framework that we discussed earlier. This is basically a repetition of what I explained earlier. So the gyroid shape easily fits within the unit cell approach. So you can easily, for example, on one hand, change the unit cell size. So if you have a very small unit cell, you can generate quite dense structure, while if your unit cell is quite large, your lattice structures are not as dense. And within the unit cell, of course, you can then change the thickness of the structures. It's basically a thicken operation on your implicit model, on your implicit function. Okay, I think we've discussed enough about the theoretical background. Let's now apply it on some use cases. The first case that I want to discuss is a liquid cooled application. So I'm not sure if you're into computers, but this is a commercial CPU cooler that we bought off the shelf, took it apart, and optimized and using Coldstream. It will mainly focus then on the heatsink for the CPU itself. We won't consider the heatsink, the heat exchanger with the air. Let's just consider this liquid heatsink part. This is an overall geometry of 60 by 40 in profile. Inlet is centered here in the middle, and the outlet is offset to a corner. We'll impose a heat source on the bottom, representing our chip, and it produces 250 watts of energy. And of course, we want to optimize the temperature of that heat source. We want to minimize it as much as possible. For coolant, we'll use a water glycol mixture with a 40-60% mixture rate. And to make sure that the pressure drop doesn't rise to infinitely high, we'll also impose a pressure drop constraint set to 11 kilopascal. And for the structures, or the TPMS structures that are made, they'll be made out of copper with a 280 micron feature size, meaning that the structures need to be at least 280 microns in thickness, but they can be bigger. And the copper that we consider has a thermal conductivity of 360 watts per meter Kelvin. And of course, whatever is open here, that's where Coldstream can generate those structures. If we optimize them for the nominal point using pins, fins, and gyroids, we get the following results. We get quite a dense structure of pins and fins, resulting in locally very low temperatures. But these structures have a downside of quite high peak temperatures, while the gyroids, or for this particular case, relatively open, not dense at all, resulting in a more uniform temperature distribution. So the overall, the lowest temperature is higher, but the higher temperature is lower compared to the more conventional cooling structures. And just because I like to show it, if you then go to, for example, true topology optimization, where you don't a priori fix the design shape, of course, you can get much more intricate looking patterns, much more organic looking patterns, and there's also a better overall performance. Okay. So that was optimized for the nominal flow condition, but not of course not everything works on the nominal flow condition. We also performed a sensitivity study to see what would happen or how these shapes perform when a different flow rate is applied. So the center one is of course our nominal condition. We had a look, we did the CFD study with a flow condition 10 times lower, so only 10% of the nominal condition, and a flow rate 4 times higher, so 400% of the normal condition. For the nominal condition, the gyroid, so the red line, the red dots, is the best performing design. But if you lower the flow rate to only 10% of the normal condition, we see that the thermal resistance increases dramatically. Same with the pins. While the fins, of course, it also increases, but not as much as the gyroids and the pins. This can be perfectly explained because the main benefit, of gyroids and pins in general is that they can break up the boundary layer and allow for mixing. But if your flow rate is quite low, you don't have that energy to introduce mixing, and then contact area becomes much more important. And the opposite holds true, of course. The higher your flow rate, the more dominant mixing becomes. In this particular example, pins start to outperform gyroids. So the main conclusion from this is, yes, gyroids are high performing, but not in all scenarios. Not for all flow conditions, sorry. Let's have a look at another case study. Now it's an air-cooled case. Again, relatively simple. We have a heatsink base positioned here with holes to fasten it down into the rest of the structure. We have a heat source on the bottom producing 5 watts of energy. Air comes in on one side and leaves through the opposite side. And we have our design main here in the middle, where we have to leave space on either side to make sure that the structures or that the heatsink can be easily fastened to the rest of the housing. And then our objectives are, of course, to reduce the temperature of the heat source. And we'll consider again pins, fins, and gyroids with a minimal feature size of 1 millimeter. And we get the following shapes. Again, a quite dense gyroid pattern, quite dense fin pattern, and the fins are non-continuous, so there is a bit of a breakup to again allow for mixing, and a relatively open pin design. If you then have a look at the CFD data, and mainly in the looking at the flow rates or the streamlines, the dense structure basically causes the flow to pipe or to leak through the sides. The density of the structures don't promote the flow through it as much. Well, fins, of course, there is still some bypass, but most of the flow can go through it. Same with pins, because the structure is not as dense. Most of the flow passes through, which of course aids in heat transfer. If you look at the raw data, let's take the pins as our reference. The fins have a slightly lower thermal conductivity. Thermal resistance, because of the increased contact area, of course, for more or less a similar pressure drop. While the gyroids, the thermal resistance is up by 6% for a much higher pressure drop. So this again shows that in certain scenarios, this is of course one specific scenario again, gyroids, despite all their promises, is not always the best solution. So when you design something, always consider other options as well, like simple pins and fins. Okay, that's everything that I wanted to cover up until this part. Let's dive into the Q&A session. Our first question comes in from Abelfals. I hope I pronounced your name correctly. And you ask, do we use NTOP for making these TPMS structures? No, we do not. So this is our in-house code that generates these structures. I hope that answers your question. Our second question comes in from Vessa. And your question comes, or is about capillary action within TPMS structures. You mean that that you have a small liquid layer or something inside of the TPMS structure, but that it's still open to the air? Is that what you mean? if so, that's not something that we looked into. So for the applications that we looked into, it's always a single fluid body without mixing. Okay, yeah. You mean like yeah, that there's phase change. You mean? Okay, that's something that we didn't look into for this particular case, but it's yeah, Colson can easily do it. We use the homogeneous equilibrium model to take boiling into account, and there's also an active research project within your university. I hope this answers your question. Then a question from Reza. Why? So you ask why the last test case that I share was not enclosed. You mean that why we allowed these bypasses around the design domain? Is that what you mean? Okay, simply because of how it should be fastened. It's a theoretical study, a fictitious case, and in this case we needed to make sure that these hole or that the heatsink itself can be easily fastened down to the rest of the body, or to the rest of the geometry. You're absolutely right. Let's say the design domain, if there were no bypass, potentially in that scenario, gyroids could be better than pins and fins. The main point was to highlight that TPMS structures are very popular these days, but are not always the best option, the best cooling solution. I hope that this answers your question. We then have a question from L. And you ask if it's possible to determine the total surface area of the TPMS structures. It would be useful to compare the surface per unit volume. That's a very good question. It is not directly available, but it's relatively easy to get to if you use full CFD at least. Any other questions, please? Also looking at the time. If not, then I will move to my final slide. I hope you found it interesting. If you would like to try Colson for your own, we do make a page available to you, or a version of Colson available to you, where you can have a look at finished demos completely free of charge. You can access it here by following this link. Or if you're interested in knowing more, you can easily contact the team by emailing to info@diabatix.com or by calling this number. That was it from my side. I hope that I will see you again in the next webinar around middle of November, around the 19th, if I'm not mistaken, and where we will cover power inverters. Okay, thank you all for your participation. I hope you learned something, and I hope to see you in the future. Have a nice day. Bye-bye.